Researchers at the CERN Particle Physics Laboratory may have discovered an entirely new natural phenomenon. When the enormous accelerator at CERN, known as the Large Hadron Collider, began operating a decade ago, there was a great deal of anticipation that new particles would soon be found that would assist us in solving some of the most perplexing problems in contemporary physics. There were several hypotheses, some of which included hidden dimensions, dark matter, and even miniature black holes. However, with the exception of the astounding finding of the Higgs boson, the research has not produced any hints as to what might lay beyond the standard model of particle physics, which is currently our best theory of the microcosmos. Want to know more? Alright, stay tuned to the future space. As a result of analyzing the billions of collisions that have occurred over the course of the past decade, we may have found evidence of something completely new, possibly the carrier of an entirely new natural force. However, there is a need for utmost prudence, which dampens some of the enthusiasm. Since the Standard Model was constructed in the 1970s, it has withstood every experimental test that has been thrown at it. Therefore, in order to argue that we are finally witnessing something that the Standard Model cannot explain, remarkable evidence is required. Strange anomaly. The Standard Model is a theory that attempts to explain nature on the most fundamental level. It is composed of fundamental particles known as leptons, such as electrons, and quarks, which can combine to form heavier particles such as protons and neutrons, as well as the forces that these particles interact with. Quarks come in a wide variety of flavors, some of which are unstable and have the potential to change into other types of particles. The net result is related to an experimental anomaly that was originally hinted at in 2014, when LHCb physicists observed beauty quarks decaying in unusual ways. This was the first time that an experimental abnormality has been hinted at. Specifically, it seemed that the rate at which beauty quarks decayed into leptons, termed muons, was lower than the rate at which they decayed into electrons. This is odd because the muon is essentially a carbon copy of the electron. They are identical in every manner, with the exception that the muon is approximately 200 times heavier than the electron. It is reasonable to anticipate that beauty quarks will decay into muons at the same rate at which they decay into electrons. The only way that these decays could occur at different rates is if some never-before-seen particles were getting involved in the decay and tipping the scales against muons. This is the only way that these decays could occur at different rates. Although the outcome for 2014 was intriguing, it was not exact enough to allow for the formation of a definitive conclusion. Since then, a number of additional anomalies have shown up in processes that are similar to this one. They have all individually been too delicate for researchers to be convinced that they were true signals of new physics, but intriguingly, they all look to be pointing in the same direction, which is a hint that new physics is on the horizon. The crucial question was whether or not these abnormalities would become more pronounced as more data was analyzed, or whether or not they would vanish altogether. The same measurement of beauty quark decay was carried out once more by LHCb in 2019, except this time it included additional data collected in 2015 and 2016. But there was not a significant improvement in the clarity of the situation from 5 years earlier. The latest findings. The addition of the sample that was recorded in 2017 and 2018 brings today's result to a total that is twice as large as the previous one. The data were analyzed blind so as not to inadvertently introduce any biases into the process. This meant that the scientists were unable to see the findings until all of the processes that were utilized in the measurement had been tested and reviewed. Mitesh Patel, a particle physicist at Imperial College London and one of the leaders of the experiment, recalled the joy he felt when the time came to look at the outcome. Patel was one of the individuals responsible for conducting the experiment. He remarked, "I was genuinely shaking," and went on to say, "I realized this was perhaps the most thrilling thing I had done in my 20 years of working in particle physics." The result was displayed on the screen, and the anomaly was still present. There were approximately 85 muon decays for every 100 electron decays. However, the uncertainty was significantly reduced in comparison to earlier. The fact that the uncertainty of the finding is now above 3 sigma which is a term used by scientists to indicate that there is only around a 1 in 1,000 chance that the result is merely a random fluke of the data, is something that will thrill many physicists, and here's why. Particle physicists use the term evidence to refer to anything with a probability of 3 sigma or above. To state with certainty that a finding has been made or an observation has been made would require a level of statistical precision known as 5 sigma. Theorists have demonstrated that it is possible to explain this anomaly, as well as others, by acknowledging the presence of brand new particles that are impacting the ways in which the quarks decay. This explanation may be applied to other anomalies as well. One of the possibilities is a fundamental particle that is referred to as a Z prime, which is, in essence, a carrier of an entirely new natural force. This force would be incredibly weak, which is why we have not observed any traces of it up until now. Additionally, electrons and muons would react to it in a different way than they do to the strong nuclear force. Another possibility is a so-called leptoquark, which is a particle that has the extraordinary property of being able to decay into both quarks and leptons at the same time. This particle might be a piece of the larger puzzle that attempts to explain why we observe the particles that we do in nature. Interpreting findings. Are there any signs that point to the existence of new physics? Well, maybe, but maybe not. At the LHC, we take a large number of measurements. Thus, it is reasonable to anticipate that at least some of them will deviate to such a great extent from the standard model. Even though this result has been checked an incredible number of times, we cannot completely rule out the potential that our experiment has some bias that we have not properly accounted for. This is because there is always a chance that we have missed something. More information will, in the end, only serve to make the whole thing more understandable. The Large Hadron Collider is currently receiving a significant modification that will significantly increase the rate at which it can record collisions. Even if the anomaly continues to exist, it is quite unlikely that it will be fully acknowledged until a separate experiment can verify the findings. There is the intriguing prospect that we could be able to identify the new particles responsible for the impact while they are being formed immediately in the collisions at the LHC, which is one of the fascinating possibilities. In the meantime, the Bell 2 experiment being conducted in Japan ought to be able to produce comparable results. What may this possibly imply for the development of fundamental physics in the future? If what we are witnessing is in fact the precursor of some new basic particles, then this will, at long last, be the breakthrough that physicists have been eagerly awaiting for the better part of 3 decades. We will have finally seen a piece of the bigger picture that extends beyond the conventional paradigm, which in the end might make it possible for us to solve a variety of mysteries that have been around for a long time. These include the nature of the Higgs boson, which is an invisible form of stuff that is thought to fill the universe, as well as the nature of dark matter. Even theorists who are trying to unite the fundamental particles and forces could use this information. Or, and this is the possibility that excites us the most, it could be directing our attention to something that we have not even considered. So, should we really get enthusiastic about this? The search is most certainly still on, as findings of this nature do not present themselves very frequently. However, we should proceed with caution and humility. The assertions we are making are remarkable, and they demand extraordinary evidence. Time and effort are the only things that will tell us whether or not we have finally caught a glimpse of what lies beyond the scope of our current understanding of particle physics. And that brings us to the end of the video. Feel free to let us know what you think about this video. And if you liked this video, then please leave a like and subscribe to our channel for more amazing content.